Okay, start MATLAB, select the directory where the software is, type guide, select the fig file, this one. So if you want to have information about guide, you can check here, getting started. And I have organized this software with tab panels. Means that when you select this one, you will have a certain panel in front of you. When you select this one, you will have another panel in front of you. So if you want to check the different panels, you need to press Ctrl B, and then you go back, then you go back again. So if, for example, you want to access the part of the code that you execute when you press this batch button, for example, you select it, right click, view callbacks, callback, and then you go to the part that you execute when you press that button. So data is organized in this way. We have a folder Pilatus 2 with all the images, so TIFF files, and then we have a folder with all the DAT files, which are these ones, so you can drag and drop into MATLAB and then you can open the file. And I have converted these files into spec files. I do this conversion, and you don't need to do that because I've already done it for you. So basically in a spec file you get, for example, date string is here, scan is here, and so on. And then you have the various columns that corresponding to the current scan that you are doing. And another important thing, we have a reference to the TIFF file, and then all the regions of interest defined during the experiment. But after you build the graphical user interface, you need to execute it with this one. This is the graphical user interface which is actually used for the analysis. So we've got the tabbed panel, which is organized according to the logical sequence of the analysis. Then we've got the typical structure of a Windows program. So we've got file import and all these things, and then we've got the toolbar here. Okay, so first thing to do is to select the spec folder, and to select the image folder. Then you need to define a working directory, select a working directory. We have chosen analysis. Okay. We observe that all the TIFF files have got this prefix P2M image and then a number, and this number is written in the DAT files here. So I do file. Suppose that we want to import this spec files, which contains all the images relative to that scan. We go to image image prefix, we write p2 image extension diff. We leave it like that. Okay. So this is a calibration scan where we move the VTTH, which is the diffractometer angle, which means that the camera was going up and down radially respect to the center of the diffractometer. So these are the supporting informations of paper that has been recently accepted in Macromolecules that have written, and the point that's it corresponds to that one, and as we move the detector we will see that point moving. And this sort of scan is fundamental for the calibration, which means for the calculation of the so-called delt x and delt y, which are the distances that you can calculate from an HTTH scan and from a VTTH scan. Now we import another file, 33, which corresponds to the HTTH scan. In fact, here we have the list of the imported spec files. So 33, and in this case we see that the beam moves from the left to the right. So now we can go on with the calibration. So get distance sample detector using those scans. I need to press 1. This will take a while. Save plot, yes. That's what you get. HTTH calibration scan and VTTH calibration scan. Let's go to the analysis folder. You will find this file that we call calibration. This is automatically generated when you do the calibration, and you will find an angle and the corresponding x pixel and y pixel, and then the other angle and the corresponding x and y pixel. So thanks to this scan you can build a triangle and calculate the distance sample detector using an HTTH calibration scan, which is this number of pixels, and you can do the same with the HTTH scan, so you will get this distance in pixels. Now we save this session, save as, we save it in analysis, calibration. So if we close the program and then we load it again, we go to File, Load Workspace, Calibration, so the session is restored. At this point we can get rid of these two scans because we don't need them for the analysis. So we go to File, delete current spec file structure, and again. So let's open the first spec file for the first sample, P3HT. this one. File, import spec file. This one. We can adjust the contrast image. So basically, the image that is displayed is converted from the original data to grayscale image with values going from 0 to 1. Here we are clipping the values from 0 to 0.12, for example, or 0.12 or 0.012. Then we can use an adaptive histogram equalization and finer filter with a window of 4 by 4. We can also rotate the image in case that the sample level is not aligned. Here we are rotating of 2 degrees, for example. You don't need that now. We can change the color map. We also observe that we have an information about the current TH value, HTTH, VTTH, time, sample temperature, and the temperature of the hot plate. If we take another image, we see TH changing because this is a TH scan. Okay, so let's consider the second sample. This one, we've got an alpha scan and a fine alpha scan for the pristine sample. The critical angle is quite high, it should be something like 0.12. Oh, that's okay. So we delete this and we import 1662 and the other one. Okay, this is nice. So we've got should be P3HT with probably PCBM. It's not written, but I suppose that this is the first ring, second ring and third ring of P3HT, but I don't know, and this is the 0 to 0 and probably this is PCBM, but I don't know. Anyway, at this point we need to detect the center. We have 3 options. The first option is the direct beam detection. Okay, let's try this process with zoom there. Here we see the direct beam. This one, we click here and then we get this stuff. We select this, we right click, crop image, and here we are. But we just note that the sample is not well aligned, so probably it's better if we go to image and we rotate the sample. So auto rotate, we go there, crop image, so this is, press yes, and then we try to apply the rotation and see whether this edge is at the same pixel of that edge. We need to calculate the center again, because once you rotate, the center is not in the same position, in the right position. Process, crop image, and then we get the center in the right position again. And so we go here and then insert center, set center, and then we batch this for all the image. So we select another image and we see if the center is in the right position, and it is. At this point we need to update POX and POY. Check the supporting information and you will see what is this. This is a kind of refinement of the calibration. Okay, once we do this update, we need to build the line profiles. Use Q values, use Q ups. You can smooth the line profile. So again, you can check the supporting information to see what is the meaning of this smoothing. Anyway, this is the smoothing window, and this is the order of the polynomial that he used to do the smoothing. So this is the radius of the line profile. So we will have a radius of 1200 pixels with an azimuthal angle of 90 degrees. We can check this. If we do 135, we will get an angle of 45 between here and there. Steps is the number of lines that are produced and then integrated in this integration slice. I usually do 30, and I usually put this range as a 10 degrees, and now it's smaller. So let's go back to 90 degrees, so out of plane line profile. Instead, when we want to do an in-plane line profile, we do 170. And here we don't do exactly 180, otherwise that's 175, otherwise that's the effect that we get this part below the sample edge. Instead, in this way, it's almost fine. Well, TH is quite high here, that's why the sample edge is so high. See the difference. Okay, so let's go back to 90 degrees. At this point we can visualize certain number of line profiles, pressing, process. So here we see the TH angle, the line profiles, and the Q values. Or we can plot this inside the graphical user interface. Or we can do a selective plot, for example 6 4 3 2 8 and 6 4 3 2. Selective. You will get x and y coordinates, so if you want to at this point we patch all the line profiles contained in this spec file. Batch. We have selected to Excel files. We need to save it. At this point we can open the Excel file, and here there are QAbs, MCCD file, which means diff file, MCCD it's the Grenoble convention, spec file, diff file, time, sample temperature and hot plate temperature, TH or alpha angle. And once you have this file, you can drag and drop it into origin. Okay, the first steps for the fitting are, the first thing to do is to define a certain number of fit blocks. We will define 1, 2, 3, 4, 5 fit blocks. To do that you need to insert 5 and then press enter. And the first fit block is the background, so you need to extract the background. You need to define a number of Gaussians. 1, you write B here and then you press enter. Then you need to go to Gauss here and insert arbitrary numbers. I know there is a bug, so you need to do that. And then you need to define the domain for the background. At this moment the domain for the background extraction is this one. We are going to use a cubic spline to fit the background, and to change this domain you just need to press if you go to profile 3 you just need to go to plot, and then you right click on the figure and you define, let's say, domain 1 left and you select it, domain 1 right and you select it and you press that, and then you leave it in this state, and then you can close this thing. Then remember to write something here, for example 0, otherwise there is another bug. You will lose the information. You can also use a special syntax Q6, which means that you can refer to the position of the sixth peak. Now we need to discuss about this. Before you extract the background, you need to detect a certain number of peaks, or well, you could extract the background without this thing, so writing just a number, but it's better to define the peaks before. So we need the 6 peaks, 1, 2, 3 PCBM 0 to 0 minimum, to define the boundaries so that the software can look for the maximum. In the case of 1, 2, 3 PCBM and 0 to 0, we need to press plot, and again we need to define left boundary, right boundary, and so on. We leave the figure in this state, and then there is an exception, this minimum. You can go to code, define a peaks rule to see that when you write like minimum or mean 1, 2, 3, the software will look for the minimum between these two values. Then if you press process, you will see minimum 1, 2, 3 PCBM and 0 to 0. So after you find these peaks, you need to batch, and then you can extract the background. So we have in green we have the fitted background, in magenta we have the residuals. So in the second block, fit block, we will fit this part, and here we are. At this point it's better to save the current section. So we go to the analysis folder and we create a new folder, and we select working directory. Okay, and then save workspace. At this point we need to define a model so that we can fit these 5 peaks. First peak, second peak, third peak, and 0 to 0. So let's consider the first peak. First peak, we can use 2 Gaussians. So remember to call them with the same name, because they will be plotted together, and the sum of these 2 Gaussians will be used to calculate the width of the peak, the integral, and the peak position. Now we need to define a domain, so we can use just one domain for this peak. Plot. So the first peak, let's take this up to here. We leave it in this state. Probably it's better to use two domains. So now we add this part and this part, and then we leave. Now you can plot the domain for the first peak. It's the thick line. Okay, so and now we can try to fit this peak. Run fit up to first peak, and we need to define the parameters. So A indicates the peak intensity, which goes from 0 up central point, P1, which is the intensity of the first detected peak, which means the intensity of this detected peak, this one, and so we can use a central point like that, high boundary like that, low boundary for the peak center Q1 times 0.99, center Q1 times 1.01, and then we can use equal, so that clearly here you have the same value that you have there. At this point we can say again fit up to the first peak process, and the fit is almost perfect. So you can see the residuals, background in green, your peak in red, and then the single peak. Here you have the diff file, domain size calculated with the Scherer equation, the Q position, the position of this peak, and the peak integral. If you want to extract the vectors which have been used to plot these graphs, select this one and then press process as I did, and then you will get this file which contains data, fitted data, fitted background, data minus background, fit minus background, and the first fitted peak. So let's do the same for the other peaks. Second peak. Observe one thing, that when we jump from the first peak to the background, this table stays in memory, so you don't need to worry about that. Second peak. We can use just one domain, and the reason is that the background extraction takes care of this rubbish. Well, I think this is rubbish. We need to put the values for the Gaussian. We do the same thing that we did for the first peak, but in this case we need to refer to the second peak, and we can try. Okay, so we've got the second fitted peak. You can start to see effects of paracrystallinity that, so 113 and 78. This indicates disorder. So let's do the third peak. We call this 3, 3. That's fine. 3. How many domains? Just one. So we will fit the third peak together with the PCBM peak. And then we will see. Okay. So again, fit. I need the PCBM. Pick 3. And these are the parameters for the width of the Gaussian. You can see this in the supporting information. So let's try to fit this. That's fine. Yes. Third peak, PCBM. So again, see the domain size. 113, first peak, 78, second peak, 59, third peak. So it's decreasing, and this is due to paracrystallinity. So long range disorder between the backbones. We don't need to fit up to the 0 to 0 because in these out of plane line profiles, we don't have any 0 to 0 peak. We will need it for the in-plane line profiles. So at this point, for example, again, we can save the fitting. and then we can check again. So data, fitted background, data minus background, fit minus background, first peak, second peak, third peak, fourth peak, which is PCBM. And for example, if you open origin, you can drag this thing there. Get rid of this. Now we can batch the fit for all these images. So we need to select this one and that one. Unselect these, otherwise you will save all the lines, like background, fitted profile. If you want, you can select that and save everything, and then you need to press batch. We see that when the angle TH becomes very small, PCBM peak disappears. You can see that from the peak integral. And finally, we don't get anything, just the first peak at very low angles. Third peak disappears. There is also to say that when the angle is very small, the intensity tends to be very low. So finally we get, oh, clearly this is an error. So finally we save everything. So you get fig files for all the fits. And you could have selected this one and you would have got the corresponding vectors to plot. This one, for example, or that one, for example. Okay, let's see what we have. You can finally save the workspace. And get rid of the previous ones. Yes. Now we can open the Excel file. The Excel file contains the line profiles, fit, so diff file, time, sample temperature, angle, domain size calculated with the Scherer equation, lattice constant calculated using 2 pi divided by the Q value in the position of the peak intensity, the peak integral, and so on. Then you get the correct domain size with the paracrystalline correction. You can see that in my paper. So basically you use this, and that to get the correct domain sizes and the degree of disorder. Okay, now we go back to profile. We select 170 for the in-plane line profiles. That's fine, because I think we will take 0.2 as a value, 0.2 or 0.25 as a value above the critical angle. The line profile is fine here, but unfortunately the user didn't optimize the position of the detector. That's strange. So basically we see the first peak is cut by the grid, this one, and the 0 to 0 as well. So for the in-plane line profiles we will need to fit this one and that one. So we batch again, we save, and I've created another folder for the in-plane line profile. So the previous results are in out of plane, and now we are working in the in-plane folder. Before changing these fit parameters, it's better to save the fit settings. We save the fit settings analysis here, fit settings out of plane here, and then when you want you can load them whenever you want. So we need to check again if the background is fine. So let's define the boundaries for the background. Domain 1 left. Okay. So we can try background. That's fine. So we need to fit just 2 peaks. 3. I need to delete this. So the background is fine, 100 is fine, let's check. Need to define again the domain for the first peak, because we should avoid the grid, and otherwise we will get an error. We go to domains, let's do 3 domains. Domain 1 left, right, 2 left, 2 right. Two domains, and okay. Let's see, it's a bit difficult because there is the grid in the middle, but it's okay, not that bad. Clearly with this thing you get just qualitative information. And now we need to work with the second this one, and this number, pick number 5. So we select this, go to this one, pick 5. Okay, then we need to define the domain, plot, left, let's say from here to, it's really in the middle, so this will be difficult. We can try. And that's the result, but well, you know, you have a large part missing. Okay, so now that we have this, we can batch the line profiles. We can batch the fit for all the TIFF images, and this time we will save the Excel files just as an example. So we start, and then clearly, if you want, you can define boundaries for the domain of the background and see if you get better results, or you can also try to use a single Gaussian and see what happens. So what we get in the end, we get again all the fitted lines for all the TIFF files. We get the corresponding fig files, so you can use this if you want to plot everything in origin. We get again this file, but clearly in this case we don't have the paracrystalline correction, because to do that we need 3 peaks. So we've got the first one and the 0 to 0. Let's just step back. And line profiles. So every time you want to plot the line profiles, you need to use the Q-abs as a x-axis. So we save this session again, and also we save the fit settings for the in-plane fit. Fit settings in plane. Okay, now let's build a grid with the x and y axis. You go to grid here. For example, you select 0.4 here, and grid on, and then generate a grid. So now, for example, you can print single image this, and you will find it here. Now that's your file with the axis, and if you want to change the way the font size and all these things. You just need to access to the code, save single image here, and then you can play with the parameters. Here you are clearly using the color maps selected here. So if you, for example, you want to create a grayscale image, you go here, and you do image, you get this. And then display grid. So yeah, you can play with the fonts of these numbers and with the fonts of QX and Y and QZ. And then if you put this to 1, you can decide if you want to display information about the sample temperature, time, reg. You can also play with the position of the figure in the fig file with these things. So you can see the MATLAB guide for the meaning of this set fig, set axis, and then finally you save. You can also display, you can select the Q values, press this one, and then get the Q value corresponding to the point where you have clicked on the image. So QX, QY, QZ, QABS, QX and Y. And you can also plot this point there. Extract 2 points, for example, one here and one there, and then you will get points. So when you open this, QX, QY, QZ, Q absolute value, and QX and Y. Other things you can do with this one, you get a snapshot of the graphical user interface. With this one you print all the images and then you get a movie. So now we are building up the movie, and then we find all the images saved and a movie. You can slow down. Okay, let's see how to crop. If you want to crop the image, you press there, select just the part that you want, find the center again, insert center, update POX and POY. Yeah, before you update you need to extend the region, otherwise you will get errors. Okay, then update. It will take a while. Generate the grid. Now you can adjust the width and the height. Don't change the first point, means 405 and 811.